Okay, let's look at a group of organic molecules called the alkanoic acids. And these all have a C double bond O and an OH group there. So they have a carbonyl group, the double bond O, and they have a hydroxy group similar to our alkanols. I like to think of these as a combination of alkanals, if we remember, have a terminal double bond oxygen, and our alkanols or our alcohols. And this particular group, the COOH, COOH, is what we know as a carboxyl group. So these have a functional group called a carboxyl group, and it must be on a terminal carbon. So how do we name alkanoic acids? Well, first of all, we must look for the longest carbon chain containing the carboxyl group, the COOH group, and we use the suffix oic acid. So we drop the E from our alkane and we put OIC for oic and then an acid. We've also got to ensure that the carboxyl group, the COOH group, will always, or must always, be at the lowest possible carbon, and because it's a terminal carbon, it must always be at carbon number 1, unless of course we get a molecule with 2 carboxylic acids in it. But let's keep it simple for the moment. So let's have a look at our molecule on the left-hand side. We have a molecule with 1, 2, 3, 4 carbons in it, so it's going to derive from butane. We name our carboxylic acid at number 1. So in this case, we're going to get butanoic. We drop the E from the butane, add the OIC, and then an acid. So this one is known as butanoic acid, also known as butyric acid, and can be found in the cheese making process, and it's also the one that sometimes teenagers produce under their armpits and in their shoes or on their feet. We've also got a second one here, has 5 carbons, has a substituent group here, a methyl group. Now, our carboxylic acid will always take precedence in the naming over any other substituent groups. So that's why we name it at number 1. So we've got 1, 2, 3, 4, 5. Position number 4 will be our methyl group. So we have 4-methyl, because it's 5 carbons, pentane, we drop the E and add the OIC, acid. So we get 4-methyl pentanoic acid. We've got a third example that's slightly more complex. So we've got a ring structure, we've got a cyclopentane aspect to this molecule, and then we've got a C double bond OH here as well. Now we said when we're naming that the carboxyl group takes precedence over everything else. So this particular molecule only has 1 carbon in the chain. This cyclic structure is a side chain to this particular chain here. And because we've only got the 1 carbon, it's a methanoic acid or methanoic acid. Methane is the 1 carbon. And we've got a side chain of a cyclopentyl group. So the 5 carbons in a chain, cyclopentyl group on the methanoic acid. So we have cyclopentyl methanoic acid. Let's have a look at some properties of alkanoic acids. They generally, compared to alkanes, they have a high boiling point and melting point because of the intermolecular forces. They have hydrogen bonding between the oxygens and the hydrogens, and the alkanes just have London dispersion forces. We've also got quite high solubility with if we've got 1 to 6 carbons in our chain for our alkanoic acid. After that, solubility starts decreasing. So how do we prepare an alkanoic acid? We start with an alkanal. So we've got the terminal double bonded oxygen here. We put it into a solution containing an oxidizing agent. We could use the chromate ion, we could use the permanganate ion, and this is acidified. And from there, we'll produce the alkanoic acid group, the COOH group that we know. Okay, let's have a look at some reactions with our carboxylic acids or our alkanoic acids. If we put our alkanoic acid into a base, it's a weak acid, so it will react, but you'll notice if we put it into the presence of an acid once again, it'll reform our alkanoic acid. But if we put it into the presence of our base, a strong base, we'll form the salt of our alkanoic acid. So our hydrogen here will be replaced by our cation of our whatever acid we're using. So in this case we've got the sodium salt of our alkanoic acid. Now this is also a process that's used to make soap as well, but we'll get onto that later. We've also got a second type of reaction, which is our test for our alkanoic acid. If we add sodium bicarbonate to our alkanoic acid, we will produce carbon dioxide, water, and the salt of our alkanoic acid. So we'll produce carbon dioxide as a gas, we'll produce water, and our salt. And a third reaction for our alkanoic acids is a reaction between the alkanoic acid and an alcohol. So we have an alkanoic acid plus an alcohol. We put this into a solution containing an acid, which acts as a catalyst, and we have to heat that solution quite vigorously, and from there we'll produce a different type of bond, which we call an ester bond, and this molecule is known as an ester. So if we have a look at what's happening, we've still got our carbon-oxygen double bond, we have our CO, and instead of having the H, we've replaced it with the R group of our alcohol. And because we've replaced this, and we've got the OH from here and the H from there, these two combine, and we form a water molecule as well. These molecules, as I said, are known as esters and are produced artificially